Today I'm going to be looking at two vectors and finding the point of intersection between the two vectors. So essentially I'm solving the system. We're going to do that using either elimination or substitution. So the first thing we're going to look at is recognizing that the x components have to equal the same x value if we're solving the system. So I can actually set these equal to each other and set up an equation. Minus 4t. So this will be my first equation, and this is my x component. If I bring my 4t over, I get 4t is equal to 17. For my y component, I will set my y's equal to each other. So for my second equation, I get 1 plus 2s is equal to 5 plus t. I rearrange that, so 2s minus t is equal to 4. So I can set those two equations together. 3s plus 4t is equal to 17. 2s minus t is equal to 4. And then for me to use either substitution or elimination, I can multiply this second one by 4. The first equation stays the same. Then I have 8s minus 4t is equal to 16. If I add those together, 11s is equal to 33, and s is equal to 3. Now I can find my t value by subbing it back into any of the equations. So if I'm going to sub this, let's say, into this equation, so 2 times 3 minus t is equal to 4. So t is equal to 2. Now remember, we're not trying to find s and t, we're just using them to find our x and y values. So if I go back to my original vector, I can find my x by using negative 2 plus s times 3. So x is equal to negative 2 plus s times 3. We found s to be 3. So we get 7. And then our y value, if I sub that back in, 1 plus s times 2. So 1 plus 3 times 2, which is also 7. So it looks like the intersection is 7, 7. Then you want to also check the second vector. I'm not going to do that in the interest of time for your video, but it does actually work. Now we're going to look at vectors in 3 dimensions and identify if they intersect, if they're parallel, or if they coincide, meaning that they're the same plane. If the lines are not coplanar, like they're not all, if the vectors are not all on the same plane, then we would identify that as skewed. So skewed lines are specifically lines that are not parallel, nor are they intersecting. The other thing I want to point out is that if lines are parallel, they're identified as having an angle between them that is 0 degrees, whereas lines that are intersecting, we can actually find the angle. So let's look at an example. The first question is saying that we have two different lines, and notice that they're on a plane because they're three-dimensional with our x, y, and z component. And the question is just asking to identify if they're parallel. So if I look at line 1, I'm going to take the direction vector, and so if you remember, our direction vector is the part that is multiplied by the s here. So the horizontal component is 2, the vertical is negative 2, and the z component, the three-dimensional, is 4. And if we're going to identify if they're parallel to each other, by definition, that just means that there needs to be a scalar multiple. So if I take the direction vector of line 2, so if this is line 2, then I have negative 1 I have 1 and -2. So the question is there a scalar multiple? Well, I'll take my x components. 2 is equal to k times -1. So k is equal to -2. Let's see if that matches for the y and the z component. -2 is equal to k, so that works. There's our y. And 4 is equal to k times -2. We divide by -2, and we get -2. So we do have a constant scalar between line 1 and line 2, therefore they're parallel. In example 3, we're given 3 different lines. The part A is asking us to identify if line 2 and 3 intersect and find the angle between them. So we're first gonna focus on line 2 and line 3. So similar to the first example, we're going to start by taking our x components and equating them. So here and here, so 1 minus t is equal to 1 plus 2t. We'll do the same for the y. 2u, sorry. T is equal to -1 minus u, so this is our y component. This is our x. And then 3 minus 2t is equal to 4 plus 3u. Then we can simplify. And this time I think I'm going to use substitution. I'm going to solve for t. So the 1's are going to cancel, and then I'm going to get -2u. I'm going to sub that into the y component. So -2u is equal to -1 minus u. If I add u, -u is equal to -1, so u is equal to 1. We can sub that into our third equation to find t. So 3 minus 2t equals 4 plus 3 times 1. So the 3's will cancel. -2t is equal to 4, and t is equal to -2. We want to check and make sure that u is equal to 1 and t is equal to -2 satisfies all 3 components. So if we plug in to the first one, 1 minus -2 is equal to 1 plus 2 times 1. 1 plus 2 is equal to 1 plus 2, so that works. So I went ahead and paused it and did the checking offline, but you can do that yourself if you like. So I plugged in the u is equal to 1 and the t is equal to 2 to each of these 3 equations that we created from our x, y, and z components. Now that we know that u is equal to 1 and t is equal to -2 satisfies, and the 3 equations, they do create a common solution. So that means that we can go ahead and actually solve for the point. So I'm going to find this point by coming back and plugging those values into, let's say, line 1. So x is equal to 1 minus -2, which is 3. Y is equal to 1. Nope. Y is equal to -2. And z equals 3 minus 2 times -2, which is 3 plus 4, 7. So the point is 3, -2, 7. That is the common point. The next part was asking us to find the angle. So if we look and take the direction vector, we have -1, 1, and -2. And I'm going to call it B, which is 2, -1, 3. And so this is just so you know, line 3, and this is line 2. Well, we need these to find the angle, so cosine theta is equal to the absolute value of the dot product over the magnitude. So we're going to multiply -1 times 2 plus 1 times -1 plus -2 times 3. That's our x, y, and z component. And we'll take the absolute value. Then I can take a, so 1 squared plus 1 squared plus 4, and 4 plus 1 plus 9, and that simplifies to be 9 over the square, oh, I am off the page, 9 over the square root of 84. If we actually find the angle, that's approximately 10.89 degrees. So for part B, the first thing we're going to do is equate, B. We're going to equate the x, y, and z for lines, let's say 1 and 3. So just how we started last time. -1 plus 2s is equal to 1 plus 2u. So 2s minus 2u is equal to 2. 1 minus 2s is equal to -1 minus u. Negative 2s plus u is equal to -2. And 1 plus 4s is equal to 4 plus 3u. 4s minus 3u is equal to 3. So if we look at, let's say, the x and the y component, and we want to solve these, we can take 2s minus 2u is equal to 2, and -2s plus u is equal to -2, so these two. And when we add them, look what happens. We end up getting -u is equal to 0. So now that we have u is equal to 0, we can solve for s. So we can actually plug it into any equation. If I plug it, because we have to check it anyways, so 4s minus 3 times 0 is equal to 3. So 4s is equal to 3, so s is equal to 3 over 4. So we want to check to see that that's the same if we plug it into the other two components. So 2s, just kidding, 2 times 3 over 4, so I'm plugging it in here with my check, minus 2 times 0 is equal to 2. So I end up getting 3 over 2 minus 0 is equal to 2. Well, those don't work. So it looks like that s value of 3/4 does not work when I plug it back into the x component. So what that means is that there is no simultaneous solution with the three equations. So before, in this other example, when we found our t value, we then plugged u and t back in, and we equated and saw that both sides were equivalent. But this time, it's not working. We found our u, we plugged it into the z component, and we found s. Then with our u and our s, we're checking to see if the left side equals the right-hand side, and I went back to the x component. Now you can plug them in wherever you want, but you need to check all three of them. So we're saying that there is no solution to the three equations. Therefore, the lines do not meet. They're not parallel, nor do they intersect. So they must, need more room, be skewed.